In the last portion of today's lecture, we're going to talk about BERT. And BERT is the language model that is probably most often used these days for real NLP tasks, although oftentimes people will use variants of BERT that are either larger, more powerful, or actually more computationally efficient and cheaper. Okay, so let's talk about BERT. BERT is basically, at a very high level, using the same principle as ELMO, but instead of using two LSTM models, it uses one transformer model. Okay, so if we wanted to just naively replace the LSTM from before with a transformer, we could just say, well, okay, the LSTM before was trained as a language model, which means that you predict the next word that's going to occur. So now you could train a transformer as a language model. Now, before we saw transformers used as sequence-to-sequence models, but remember, in a sequence-to-sequence model, the encoder reads in a sequence, and the decoder is essentially a conditioned language model. So the decoder of the classic transformer is already a conditioned language model, so all we have to do to get an unconditioned language model is just use that same decoder, but remove the conditioning. And what was responsible for the conditioning? Well, it was the cross-attention. So if we just remove the cross-attention from the regular transformer decoder, that is now a basic language model. So we take all of the tokens in our sentence and their position encoding. We pass them through masked self-attention. Remember, in the decoder we have masked self-attention, and that prevents the future tokens from influencing the past. And then we have a position-wise nonlinearity, and this is a block that is repeated n times, right? We don't have the cross-attention anymore. So we need the masked attention because we're taking the decoder part of the transform. And then we have a position-wise softmax to predict the next word. So this would be the most direct and obvious way to take essentially ELMO and replace the LSTM with a transformer. Just use the decoder part of the regular transformer. Now this model has a direction. Just like the LSTM runs forward, this model runs forward because of the masked self-attention. ELMO is bidirectional. This thing is not. Although, if you wanted to, you could just, the same way as ELMO, you could train two transformers, one going forward and one going backward, and in principle, that would be the most direct analog to ELMO. That would be like the transformer ELMO. But is there a better way to do this? So we could do transformer ELMO. We could just have a forward transformer and a backward transformer. But could we simply remove the mask in self-attention and have one transformer? Self-attention already carries information both forward and backward. So it seems like if we just remove the mask, we would get a bidirectional model without having to go through the trouble of training two separate models. Does that work? What could go wrong with this? So take a moment to think about this. If we're to train a language model, so a language model takes as input the tokens in a sentence, and its output at every time step is the next token. So that means that the full output sequence is just the input sequence shifted over by one. So if we do this, and we remove the mask in self-attention, so we have full self-attention like in the encoder for the transformer, what will go wrong? Why would this not make a good language model? Well, the issue if we were to do this, if we were to remove the masking from the self-attention, is that the output at time step 1 is actually the same as the input at time step 2. So that means that the transformer here doesn't have to do a lot of work. All it has to do is just learn to look up the next word and copy it and output it without understanding anything about what it means. It's just like, if I were to give you a sentence in a foreign language that you don't know how to read, and I asked you to perform some transformation on it. If the transformation was to just shift everything by one word, you could shift everything by one word without really understanding the sentence at all, with the exception of the very last word. The very last word you'd have to figure out, but if you have very long sentences, that very last word has minimal effect. So just removing masking from self-attention is not a good idea because the task becomes too easy, it's too trivial for the transformer to learn how to shift things without learning what they mean. It's trivially easy to get the right answer since the self-attention can access the right answer at time t from the input at time t plus 1. And that's a big problem. So what BERT does is slightly modify the training procedure to avoid this issue. Okay, so we're not going to even do the shifting thing, right? So the output at time step 1 is actually exactly the same as the input at time step 1. But we're instead going to modify the inputs a little bit to make the task for the transformer a lot harder. what we're going to do is we'll randomly mask out input tokens. So for every token in the input, with 15% probability, we'll replace that token with some special token that has no meaning. We'll call it the mask token. All right, so all the mask tokens are identical to one another. Maybe they're just vectors that have like 1, 0, 0, 0, 0, 0. And for every token in the input with 15% probability, it gets replaced by the mask token. But the output stays the same. So it essentially forces the transformer to solve a kind of fill-in-the-blanks task. So there's no need to shift anymore at the top, and there's no masking. So an example of a problem this transformer needs to solve is it gets an input, I mask, therefore I mask. And it has to predict what words go into those slots, and the correct output is I think, therefore I am. And the intuition is that if the transformer can solve this problem, if it can learn to fill in the masked words, it has to really learn something about the meaning of the words. This intuition is very much the same as the intuition of word2vec, that if you can predict a word from its context words, then you can learn something about meaning. Although, of course, here, just like in Elmo, the word is specific to that sentence. So the main idea is that needing to predict missing words forces the model to work hard to learn a good representation, without the need for masked self-attention. So it's a bidirectional model, but it doesn't require training two separate models. So this makes it bidirectional. Another way to think about BERT is that BERT is essentially the encoder part of a transformer, with 15% of the inputs replaced with mask, and with a loss to predict the unmasked inputs. So the naive way of using a transformer that I had on the previous slide was basically the decoder part of a transformer, whereas here we have the encoder part of a transformer. So no masking, just regular self-attention. Okay, now to actually truly train BERT, there are a few little changes that need to be made that turn out to make things work a lot better. So we've got our masked language model, which I described before. So here you reconstruct all the tokens at each time step, but the inputs don't always contain the full tokens. They are sometimes replaced with mask. So you basically have to predict the actual token in place of mask. So this forces learning context-dependent word-level representations. But then we also train BERT on pairs of sentences. So we have our large corpus of text, a bunch of text from Wikipedia or newspapers or something, and we take pairs of sentences. And we always train it on two sentences stapled together. The first sentence starts with that CLS token, and the second sentence starts with the SCP, the separator token. Why two sentences? Well, it's because a lot of tasks that we want to solve involve pairs of sentences. Question and answer, paragraph and summary, English and French. Although, again, for machine translation, it's actually not such a great choice. So that's why we want two sentences. And what we're going to do with those two sentences is, we're going to train on them, but we're also going to have a special output at that first token. So the first input is a CLS token, and the output is going to be making a prediction. I'll tell you what the prediction is in a second, but first let me tell you how the input sentences are transformed. So for each pair of input sentences, we're going to randomly replace 15% of the tokens with mask, and this is done independently for each token. And we'll also randomly swap the order of the two sentences. So if in the real text, sentence A follows sentence B, half the time we'll actually feed in BA, and half the time we'll feed in AB. And then this first output, the output of the first token, will actually be a binary classifier. And it'll be trained to predict whether the first sentence follows the second or vice versa. So it's a special position. For all the other positions, we'll be predicting what the word should be at that position. But for the first position, it'll be this binary classifier that will predict true or false, depending on whether A follows B or vice versa. And the intuition for why we're doing this is because we want this first position to represent sentence-level representations. So for tasks that require token-level representations, we'll use the features at each individual position. But for tasks that require sentence-level representations, we'll actually use this first position. So essentially, BERT is doing two jobs. BERT is very hardworking. BERT has to represent words in some semantically meaningful way, and also actually has to represent sentences in some semantically meaningful way due to having to solve this permutation problem. So that actually provides us with different ways to use BERT. One of the ways that we can use BERT is if your task is a classification task, you can simply take this first position and replace it with a classifier that you want. So you train BERT on a large corpus of unlabeled text to be a good language model and a good sentence order predictor. And then you take that model and you put a new loss on the first position, which is the classification loss for whatever problem you want to solve. Like entailment classification, semantic equivalence. Semantic equivalence means given two sentences, are they the same? Do they have the same meaning? Sentiment classification, and so on. So if these are problems where you take a sentence or two sentences as input and you produce a class label as output, then you can use that first position. So you put a cross-entropy loss on only the first output, and then you fine-tune the whole model end-to-end on this new task. So fine-tune just means train it some more on that new task. So if your problem is a text classification problem, like entailment classification, semantic equivalence, sentiment classification, etc., train BERT normally as a language model and this ABBA predictor, and then take the resulting model, replace the loss on the first position with your desired classification loss, remove all the other losses, no more language model losses, and then continue training the whole thing on your task. Okay. So whether you have a sentence pair classification task or a single sentence classification task, there are many different tasks like this. This is what you would do. These are classification tasks. Now you can also use BERT for tasks that require outputting something per position. So for example, the question answering task, SWOT version 1.1, requires highlighting which part of a paragraph contains an answer. So you read in a question, then you read in a paragraph, and at the output, you're supposed to say where the answer to that question is in the paragraph. So then you output the start and end as output tokens. The way you do it, same exact way as classification, just replace the loss at those positions with a loss that you want, and then fine-tune the whole thing, basically continue training the whole thing. Single sentence tagging, so this is named entity recognition. Here the goal is for every token, output a class for that token, which is which type of entity it corresponds to, like a person name, a location, or some other category. So it's essentially a label at every position. Same exact deal, just replace the language model loss with the loss that you want at every position, and then fine-tune the whole thing. Now, you can also use BERT the same way as Elmo. So you could actually pull out features from BERT. The way you do this is you just pull out the hidden states at each position from the transformer. Now, BERT is a very large transformer model. It actually has 12 of these blocks. So it's a complex question as to which layer to use. You could use just the top layer like in simple Elmo, or you can construct a linear combination, basically a weighted sum of all the layers. And people have actually experimented with various combinations. Many of these combinations work very well. So here you have the named entity recognition task, and on the right-hand side you have a F1 score. This is essentially how well the model performs using that representation. Higher is better. And you can see that if you use the first layer, that's not very good. If you use the last layer, that's quite a bit better. If you sum all the layers, that's a little bit better yet. If you use the second to last layer, for some reason, that's actually even better. If you sum the last 4 hidden layers, that's even better. But if you concatenate the last 4 hidden layers, that actually gives the best results. So what's the lesson from this? Well, probably the lesson is that concatenating upper layers of the network seems to produce good representations. But in general, many of these truths are pretty good. Now, whether you use BERT with fine-tuning or whether you pull representations out of it, one of the kind of important lessons to take away from this part of the lecture is that generally BERT works very well. So here you can see a number of different tasks from the GLUE benchmark. So this is a benchmark that kind of presents a battery of different natural language understanding tasks. I believe all of these are actually classification tasks, but I'm not completely sure. And what you can see here is that the two BERT models, BERT base and BERT large, perform very, very well. So in the second row, you can see Elmo. In the third row, GPT, which is basically a forward language model with a transformer. BERT does quite a lot better across all of these. So BERT base has 12 layers, BERT large has 24 layers. And when I say layer, I really mean that whole block, self-attention and position-wise nonlinear network. So these are very large improvements across a range of all these tasks, and it doesn't end there. Since then, BERT has been applied to nearly every NLP task you can imagine, and often makes a huge difference in performance. So pre-training this bidirectional transformer on a large text corpus makes a really big difference for the performance of downstream tasks when you fine-tune from BERT, or even when you just use the representations in it. Okay, now, just as an aside, I do want to mention that people have successfully used the more forward type of transformer model. So this is basically like the decoder, one-direction forward transformer models. They can serve as good language models. They can serve to get good features, although not as good as BERT. But they do have one big advantage. Can you guess what that advantage is? So the big advantage of forward models, rather than bidirectional models like BERT, is that generation is not really possible with BERT. Because BERT learns to fill in the blanks. It doesn't learn to generate one token at a time to complete an entire sentence. But a forward mass attention model can actually do generation as well. So BERT, not really very good for generation, but a forward model like GPT, by the way, it's basically just the decoder of a transformer without cross-attention and with more layers. So there's nothing new about it. It's just like it's exactly the transformer, but without the encoder and without cross-attention. So classic examples of these kind of forward transformer models are GPT, GPT-2, and GPT-3. They don't really do anything particularly novel. They just have more layers, basically. But they can actually generate very nice text. So this is an example that I showed a few lectures ago of text generated to complete a prompt. So the input is provided to the model, and then the model is asked to output the next tokens. The input is something a person wrote. They wrote, "In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that unicorns spoke perfect English." Okay, that was a person wrote that. But then the model is outputting the rest of the words. So the model then outputs, "The scientists named the population after their distinctive horn, Ovid's unicorn. These four-horned silver-white unicorns were previously unknown to science. Now, after almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved." So these words were produced by the model, and one of the things that's kind of interesting about it, and that we wouldn't expect from something like an RNN or LSTM model, is that it exhibits long-term structure. So it figures out, for example, that an appropriate university would be the University of La Paz, probably because it looked at the phrase Andes Mountains in the input, right? So there are some long-term connections, and that's made very easy by the transformer because the self-attention mechanism can see an earlier word just as easily as it can see a later word. Okay, so a summary of the language models that I discussed. BERT is a bidirectional transformer. So BERT is not trained in quite the same way as other language models. It's actually trained with masked out tokens and then has to fill in those blanks. The other ones are all more traditional language models that are trained to predict the next token given the previous tokens. So GPT is a one-directional transformer, and Elmo just trains 2 completely separate models, one predicting forward and one predicting backward. BERT produces really great representations that have been tremendously useful for a wide range of NLP tasks, but it can't generate text. GPT can generate text, but its representations, as far as I know, are not quite as nice for downstream tasks. Elmo produces representations that are kind of okay, and it's generally been largely supplanted by BERT. The main reason we covered it in this lecture was just because it provides kind of a nicer intro to the concept of using pre-trained language models in NLP. All right, so the takeaways that I want to leave you with is that language models can be trained on very large and unlabeled data sets of text, like all of Wikipedia. Often these are hundreds or even thousands of millions of sentences. Internal learned representations in these models depend on context. The meaning of a word is informed by the whole sentence. And they can even give us representations of entire sentences, like the first output token for BERT. And they can be used to either extract representation to replace standard word embeddings, or directly fine-tuned on downstream tasks, which means we modify all the weights in the whole language model rather than just using the pre-trained model hidden states. And these things are very important for modern NLP because they work extremely well. So chances are, if you want state-of-the-art results in an NLP task, you're probably going to be using a language model to get your initial representation or to pre-train your model.